Okay, so on the second half of the sheet, on the back side there, level 2 gets a little bit harder because it involves more math than just addition and subtraction. It says that for part 4A, we're going to assume that he's got a mass of 100 kilograms. Let's work with the fact that G is basically 10 meters per second squared. And then they want to know the height of the building. So if we take our equation, gravitational potential energy is mass times gravity times height, and rearrange it to solve for height, height will equal the gravitational potential energy divided by mass times gravity. And now we sort of have an equation that we can use over and over again. So if we plug in for this particular case, up on top, 10,000 joules is the gravitational potential energy. His mass is 100, gravity is 10, and if we work that out, we will get 10 meters for the height of the tower up there. Then they say for the next part, well, what is the height of the circle? So that is for 4B, and if you see over here, the circle, we can do the exact same thing, but our gravitational potential energy is 6,400. So the height will equal our gravitational potential energy divided by 100, that's the mass, and then 10 for gravity. And if we work that out, then we get 6.4 meters for the height of the circle. Then for part C, they throw just a little bit more of a wrench into it, and they say, well, what is his height when his kinetic energy is 7,700? So remember that we have to have a total of 10,000 joules of energy. So his gravitational potential energy at that point would be 3,300 joules to get us to a total of 10,000. And then we plug it in there. Height would be our gravitational potential energy divided by his mass divided by acceleration due to gravity, and you'd get 3.3 meters for that part. Then what they do is they go to level 3, which is speed. It's level 3, it's a little bit harder just basically because of the square there. So it says, what is his impact speed when he hits the ground? Well, we know that kinetic energy is 1/2 times mass times velocity squared. If we rearrange that equation to solve for velocity, we'll get 2 times kinetic energy divided by the mass square root of all of that. So if we look down here when he's on the ground, he had 10,000 joules of kinetic energy. So we'll plug that in there. Velocity is equal to 2 times 10,000 joules of kinetic energy divided by his mass of 100. And if you work all of that out, then you'll get approximately 14 meters per second. So then they say, what is his speed halfway down? So you would apply the exact same technique. Halfway down, his kinetic energy is only going to be 5,000. And so divided by his mass, square root of all of that. Now you may think that would just be half the speed, that would be 7. But the square root throws that proportionality off, so it's not. Halfway down is 10 meters per second when you work out the math, not 7 meters per second. So then part C says they throw a little bit of a wrench in here again by saying, what is his speed? Whoops, made all these marks in here. When his potential energy is 8,100. So if his potential energy is 8,100 joules, then that means his kinetic energy's got to be the remainder of that, 1,900 joules of kinetic energy. So we'll plug that into the equation we built on the other page. Kinetic energy is velocity is 2 times kinetic energy over mass, square root of all of that. So we'll do 2 times 1,900 divided by 100, and we will get for his velocity about 6.2 meters per second. Then level 5 or level 4 is speed to height. So they say when he's moving at 5 meters per second, what will his height be? So to do this one, first we got to find the kinetic energy. So 1/2 mv squared, we'll plug it in. His mass is 100, his velocity is 5. Don't forget to square it, and you will get 1,250 joules of kinetic energy. That means that the gravitational potential energy to get us back to 10,000 has got to be 8,750 joules of potential energy. And now we can set that equal to mass times gravity times height, and we can solve for the height. Remember, that's 100, that's 10. So to solve for the height then, when you work that out, you would get about 8.8 meters, rounding off there. Really 8.75 meters. So then last problem here, level 5. And again, the only reason it's harder than what we just did was because we are involving a square. They say, what is his speed when he's 2.4 meters above the ground? So for level 5 here, we got to say, all right, we can find the gravitational potential energy by doing mass times gravity times height. So 100 times 10 times his height, which is 2.4, and we'll get 2,400 joules of potential energy, which means the rest of it's got to be kinetic. So that is going to be 7,600 joules of kinetic. And we want to figure out a speed, so we set that equal to 1/2 times his mass times velocity squared. So again, if we rearrange it, we'll get the velocity is equal to 2 times kinetic energy over the mass, square root of all of that, and then plug those numbers in there. So 2 times 7,600 over 100, and you'll get about 12 meters per second there. The last question says, down here, in the end, he'll stop in the pool. So where does all that kinetic energy go? He had 10,000. Well, it goes into the water. The water will heat up, the water will splash out with some kinetic energy itself there. Sound, that's vibration of the air molecules there. The energy will go into that. Whole heat up a little bit. And so all of that, even if you ignore air resistance, is where the energy goes in the end.